Log on, tune in, find out. Another good idea from Cambridge.
Nathaniel Pillai and Gareth Roberts and Andrew Stewart. Andrew Stewart is now entering the room. Is this better? So thank you very much. The problem I'm going to tackle here is that of sampling from a probability density function, pi, that lives in Rn. Well, at the outset, maybe you don't think this is related to high oscillations, but in fact it is, and this will become even clearer at the next talk by Andrew Stewart. So the topic is really related to the integration of Hamiltonian dynamics in the highly oscillatory settings for reasons that I hope will become apparent as the talk goes along. And this density function pi is written as the exponential. You can always do this because this is positive, and also in many applications, like in the talk Dr. Lelièvre presented in the morning, the density appears in a natural way as the exponential of the negative of a potential. So this would be, for instance, the case in statistical mechanics, but here the density could be arising in any kind of applications, for instance, in Bayesian statistics. So our aim is to construct samples that come from this distribution. If n were 1, you could think that we wanted to construct a random number generator, and this is like a random vector generator. We want to generate vectors in Rn that come from this distribution. And the Markov chain Monte Carlo methods construct a Markov chain. So we start from state q naught, a vector in Rn, and from here, by using some random procedure, we will jump into another state, q1 and then q2, and this chain will have pi, which is our target density, as an invariant density. And the hope is that after some so-called burn-in steps, the vectors that we generate in this way will in fact be distributed according to our target distribution pi. And I will now give some examples of this technique. So the simplest and oldest way of doing this was introduced by Metropolis and his co-workers in 1953. This is one of the, I think, is of the most widely cited papers in the scientific literature, and maybe one of the widest used algorithms in the whole of mathematics. And the procedure is as follows. Assume that I am at a current location, capital Q, so this is Rn, and I'm here sitting at the current location, and the chain will take step to a different location, Q prime. So I jump to Q prime, right? And this distance and direction are chosen from as given there as a scaling parameter, a square root of h, and then this random vector, this z or z that comes typically from a normal distribution. So I'm here, I have this so-called proposal, the random walk wants me to move here, but I'm not going to stay here. When I reach my destination, I'm going to flip a special coin, and sometimes I will stay at the proposals, and sometimes I will stay at the point where I come from. So, so there's this so-called Metropolis-Hastings rules defined by this. So I'm going to compare the target probability at the proposal, at the point I've reached, Q prime, with my probability at the old point. And the thing is that if thing is accepted, Q prime will be my next state. But if it's rejected, I'll stay at the point where I started. So for those of you who are not very familiar with this, once more, I stay here. There's a random motion. I come here. This random motion has nothing to do with my target distribution. And now I look, is my current location more probable or less probable than it was at the beginning? If I move to a point of more probability, according to my target distribution, I will stay here for the next step. But if I move to a point with a smaller probability, then in some cases, by flipping a coin, I accept the move, and in some cases, I will reject. And then the magic of this technique is that by doing so, the vectors that I generate are in fact distributed according to my target distribution pi. Now the problem with this technique, so this generates a random vector generator for any distribution in any Rn, just by starting from a normal distribution proposal. So that's the good news. The bad news is that if my jump to the proposal is a very large one, typically I will be rejected, because typically I will move to a point of low probability. I don't want to be there, so I have to stay at the beginning, right? On the other hand, if I'm very conservative and this parameter h is small, I'm a very cautious person, then I will be accepted, but of course the vectors I generate will be highly correlated. I want to make much progress. If I want to explore, as in Dr. Lelievre's talk in the morning, a very difficult distribution, it will take me ages to go to all locations in phase space. And so these difficulties of the random walk become more prominent if the dimension n of the phase space or the state space is high. And this is precisely the situation that we are interested in here. So to alleviate this difficulty with the random walk algorithm, other algorithms have been suggested in the literature. And here we're interested in so-called the MALA, Metropolis Adjusted Langevin algorithm. And here, this is the recipe for the proposal. As before, we've got a random component, so I'm here, and randomly I could jump there, or to the left, to the right, anywhere. So this is the random part. But please note that now there's a deterministic, non-random contribution to my motion. And because I'm taking this vector in the direction of steepest ascent of my probability, this component here, this vector here, will cause me to move preferably in directions towards a higher probability, so that this skews the, so to speak, the random walk, and makes it more likely that I will go to locations of destinations with higher probability. Therefore, this one hopes that this alleviates the random walk mechanism. So in the morning, we saw this Langevin equation that corresponds to what physicists would call an overdamped Langevin dynamics. And this particular stochastic differential equation has our target probability pi as an invariant measure. And therefore, you can easily relate those two. This is nothing but the Euler-Maruyama discretization of this. So we take a step. This would be our proposal. But to make sure that we are sampling from the target probability distribution is not enough to make the proposal. You have to introduce an accept reject mechanism that ensures that the target density is an exact invariant density for our Markov chain. So the third and last method I'm going to consider in this talk is the hybrid Monte Carlo method. This was introduced by Duan and his co-workers in 1987 and is widely used in molecular dynamics and other applications in physics and chemistry. If you look at it in the application where it appeared, it looks natural. For a general probability distribution, looks very artificial. So what I have to do here, recall this is our negative logarithm of the density here. So you have to construct a Hamiltonian function. So this is where the high oscillations start coming in to the problem. So we now think of this as being a potential energy, and we construct a Hamiltonian by introducing the momenta, the vector of momenta p with the same dimensionality of q. This is the mass matrix, and this is the inner product. And with this Hamiltonian, of course, we've got the canonical equations of motions as given there. So this is really Newton second's law, and this is of course the definition of the momentum. And with this system of differential equations, we consider the corresponding solution flow. And as everybody knows, this solution flow that maps our initial condition into the values of the solutions as time t has manifold interesting properties, and we are here concerned with three of them. So first of all, our solution flow preserves the value of the Hamiltonian, which is conservation of energy in physical terms. It also preserves the Lebesgue volume element in phase space, which is the Liouville property, and it's reversible with respect to flipping the sign of the momentum. So here I've got a simple example because this will be useful later. This is the Q, this is the position, this is the axis where my probability distribution sits. Here I'm considering a double well potential, so you can find an eraser somewhere. Yeah. So this is a scalar. This is the q-axis, and this is my probability. So this is bimodal. So this is an area of high probability in the q-axis, and this is an area of high probability, and here this is a location with a low probability, and this is the corresponding. Is the mic still okay? Yeah. Thank you. And this is the dynamics in the phase space, and the reversibility, of course, means that if I go from this value of q to that value of q by using this initial velocity, so that the solution flows, well, my hand is not good enough, from x to that other location there. If I reverse the velocity and I start from there but with the opposite velocity, then I will go back to the starting point, right? So there's this symmetry that will be very important later on. So because the Hamiltonian flow preserves the value of the Hamiltonian function and also preserves the Lebesgue measure, it will preserve any probability or any density that is a function of h. So that you see in particular, it will preserve this, but by definition of my Hamiltonian, this is my original target on the q, and this is the part that comes from the kinetic. So this splits because the Hamiltonian is separable. In probability terms, the p and the q are independent random variables, and because I'm conserving the joint density, I conserve both marginal distributions. In particular, I'm conserving, well, I'm not, but the flow is conserving the marginal on Q, which is my target density. So this is telling us that the flow used with any fixed, arbitrarily fixed value of T may be used to build a Markov chain for Q. So this hopefully will become clearer in this picture again. So now the Markov chain is as follows. Say this is my current location along the Q axis. So I pick up a random value of the velocity, say I'm there. I flow with the Hamiltonian flow, I'm going there. I discard this value of P, which does nothing for me, but I look at the value of Q, and then this will be my next location in the Markov chain. So if this guy happens to be distributed to my target distribution pi, the same will be true of that guy. And you see the advantage of this, as compared to the random walk and to Mala, is that by choosing T suitably, this has the potential of making global moves in the configuration space, right? So this is related to something you heard in the morning. I'm at that location of high probability there. If I use random walk, I'm going to stay there because this is high probability. If I use Mala, the same will happen. But if I use this hybrid Monte Carlo, I got the possibility, as depicted here, of flowing from that point to that point. So I can make big jumps. I go from a mode of my distribution to a different mode. So if this were a problem in molecular dynamics, I could maybe jump from a configuration to another stable configurations, avoiding any intermediate saddle points or ridges or metastable things like that. So this is the idea of the method. Of course, typically, because the distribution of P is normal itself, typically I will make small moves along the P, and then the Hamiltonian dynamics keeps me there, but occasionally I will pick up enough initial velocity for the method to go there. So this is the basic ingredient of the hybrid Monte Carlo method, but of course the trouble with the method as I have presented it so far is that in practice we don't know exactly the Hamiltonian flow. We don't have a formula for phi. But then this is why some of us are numerical analysts. We can obtain it approximately, and by a numerical simulation. The method of choice is the Verlet algorithm, but there are more sophisticated methods, and I think maybe Andrew will be saying something along those lines later on. So this is one step of the so-called velocity Verlet that moves from my initial condition to an approximation at time h. And of course, in the hybrid Monte Carlo, I want to go to time capital T, so I have to take T over h Verlet steps, and I call the corresponding map this psi. So this is the true flow, and it's approximating by T over h steps of length h of the Verlet algorithm. So now, due to the discretization errors, energy is not preserved exactly, and I have to reintroduce an accept-reject Metropolis-Hastings mechanism that will ensure that even in the presence of the discretization errors from the Verlet algorithm, the algorithm preserves exactly the target measure. So the recipe for the accept-reject is given there. It's just a matter of comparing my current energy, well, the old energy, with the energy in the proposal. So this is the picture we've seen maybe twice before. Before I moved from there, I'm there. P is an auxiliary variable. I just want to sample this density in Q. So this is my current position. I draw a velocity, an initial velocity. This gives me this point in phase space. My energy is a half there. Before, I was flowing with the exact Hamiltonian, so I'll end up with the same energy. And if I could do that, that would preserve exactly the invariant distribution. But now I introduce an error and say I'll end up at this quadrangle, this lozenge or whatsoever, where the energy is slightly larger, or 0.6. So I subtract both energies, 0.6 minus 0.5. This gives me 0.1. So the exponential is 0.9. So 9 out of 10 times that this happens, I will accept the step and I will jump to this location, even though it's less probable because it has more energy. And 1 out of every 10 times, I will reject the step and I will stay there, so that I will have to redraw a different velocity and move. And of course, the Verlet algorithm doesn't preserve energy exactly. This is why I'm doing all of this accept, reject, but it is volume preserving and it is time reversible, which means that, as it was the case for the true solution of the Hamiltonian problem, if I'm there with that initial velocity, the Verlet sends me there. Well, if I started from there and I took the opposite initial velocity, the Verlet algorithm would complete a symmetric figure. So if this goes to that by Verlet, this goes to that by Verlet. But so in this case, please note that this is too complicated for me. So here I increase energy, there I decrease energy. So this such a proposal will always be accepted because I go to destinations of lower energy, higher probability. So this is the setup. Now, what's the problem we want to solve? So here we want to investigate the behavior of these algorithms when the dimensionality of the state space, this capital N, is very large. So applications where you want to sample in state space that have many dimensions are, of course, molecular dynamics. This is where the hybrid Monte Carlo originated. This has been explained very well in the morning, so I don't need to go into this. But there are other applications of much interest in statistics and data simulations and meteorology and so on. There, the true target, the thing you want to find, is not a vector, it's a function. For instance, the initial condition for a PDE, right? This is your target. You have to discretize it, and you discretize it if it's, say, the initial distribution of the weather. They may be, you've got 100 million, a vector with 100 million components, and this is now your current target. So you have to operate in that context in situations where the dimensionality is very high. So the problem here is, how do these algorithms perform when the state space is of a very high dimensionality? Well, this is a very difficult problem. One cannot solve it, and of course one tries to solve a simplified problem. So one looks at the situation in this simplified scenario where our distribution is just a product of, so this vector Q is a product of identically distributed components. This is, of course, very simple. This is the case where analysis can be carried out, but can be extended to more general scenarios theoretically by analysis, by changing the variables and so on. This is one consideration. And also it's important to mention that the results that one can prove analytically, mathematically, for this simplified scenario appeared to carry through to more general applications when one tries these things in the computer. So this line of research was pioneered by Roberts and his co-workers about 10 years ago, and what they found for the random walk and formula is as follows. If you have the random walk, and D is essentially the dimensionality of the problem, so the number of copies of your, so N is the dimensionality of the problem, And in this, this is a bit confusing. So for all purposes, D, you think that D is n. There's a slight wider generality here, but maybe this is too complicated. So D, let's just think as D as the dimensionality. So this shows that, they showed that if you scale this parameter h in the algorithm to be proportional to 1 over your number of degrees of freedom, then you will find that in the limit where the number of degrees of freedom d goes to infinity, the acceptance probability will be non-trivial, will not be 0. Okay, so to make this maybe more clear, if I take this length of my step, a constant, say, and I increase the dimensionality of the problem, I will find that I'm rejected and rejected more and more often, and then the algorithm doesn't make any progress. So what this result tells me is that whenever I double the dimensionality of the problem, I should be more modest, and I should halve the variance of my step in the random walk. Maybe what I'm now going to say is not politically correct and can be misunderstood in various ways, but anyway, I'm going to tell you this. When I was a teenager in Spain, on a Sunday in my village, we had to go to a dancing. And in those days, all girls would be waiting there for you. So you have to ask them to dance. They couldn't ask you to dance. So there was the privilege of the boys. We could choose where to go, but they had the privilege of saying no. And typically they said no. I mean, accordingly. So you see, if you were very ambitious, and maybe you understand me, you were very ambitious, you didn't make any progress in the dance because they always say no. If you were not very ambitious, then you would always be accepted, but then you wouldn't be very happy at the end of the dancing. So this is the sense of compromise here, right? So if my age is very ambitious, I move, but I'm rejected. But if I'm very conservative, I'm accepted, but what I get, I don't like. Okay? It's the same. And here, the magic. No, I'm not going to take any jokes on this area. I mean, I said this joke privately to one of my co-authors, and then he suggested I should tell it here, but I was reluctant to do so. You know me, and you know I don't like this kind of joke, so I won't take any jokes. Maybe later, privately, I'll be happy to. Okay, so this is the end of the dancing. At least in Spain these days, you have to be very, very careful with this sort of thing. When you, so you get me into trouble.
Spain's catching up with the rest of the world. That's good.
Okay, so here the recipe is that for the random walk, each time you double the dimensionality, you should halve. So the method becomes more expensive. And the second part of this result, which is very nice, is that regardless of your distribution, there's a magic value of the acceptance probability, which turns out to be 0.234. And when you choose the parameters in the method so that you observe that your acceptance ratio is close to 1/4, this is your optimal thing. If you see that you are accepted too often, this is an indication that you are not ambitious and you are not moving far enough, right? And if you see that you are accepted less than this, then this means that that you are being too ambitious, and of course you are stuck with a lot of rejections, and this is not. So this is, and of course the beauty of these results by Roberts and his co-workers is that this is completely independent of the target distribution. So for Mala, the situation is better because we now are inputting information on the likelihood in the algorithm. So we are using the gradients of the probability to guide our motion in state space. So now, rather than scaling h as 1/d, you have to scale as 1/d to the cubic root of d. So that now to reduce h by half, you can afford to increase the dimensionality of the problem by a factor of 8. And again, there's a magic value for the acceptance probability, and this is roughly 0.574. So the exact value, the fact that this is a half and the other is a quarter, is not relevant. What's relevant here is that those values are universal. They don't depend on the distribution, and you can use it as a metric to ascertain whether you are being too ambitious or too conservative, right? So you got something to guide your parameter choice when you apply the method. So the problem we once solved in this talk was the situation for the hybrid Monte Carlo method. So the result. So we will prove here, and as I said, our findings will match experiments and heuristics by different groups of people, that in the hybrid Monte Carlo method you have to scale h by this factor, which is slightly better than in Mala. So if you adjust the step length in the Verlet algorithm by using this recipe, L is an arbitrary constant that you're free to choose, but here each time you multiply the dimensionality by 16, you have your Verlet step, you will be in business, because you will see that the acceptance ratio that you get approaches a non-trivial value, something which is not 0 and is not 1. And the speed of exploration of state space is optimal when you observe this acceptance ratio, roughly 2/3. Again, it's not very important, that's 2/3, a half, a quarter. What's important that we've got a yardstick to ascertain whether we are being very aggressive in our proposals or otherwise. So what remains of the talk, I'm going to show you the proof of this result. Well, the whole proof is extremely technical, so it requires a lot of numerical analysis. So I'll spare you the details, but I'll give you the main ideas, and I think those are nice ideas from geometric integrations, and I think everybody will understand this if I'm capable of putting it across in a right way. So we are going to look at the hybrid Monte Carlo method, but recall we are now in a simplified scenario where the vector Q, the components are random variables that are independent and equally distributed, and accordingly you see this is my state variable Q. This comprises d copies of this Q or Qi. So this Qi, the individual component, is small. The aggregate is large, and I will do the same for the velocities or the momenta, and I will call X the combination QP, and with capital P, and same for the small letters. So because I'm in this simplified scenario, my Hamiltonian for the aggregate is just a sum of Hamiltonians for the individual particles. So each individual particles, and I've got a d of them, moves under this potential and has this mass matrix. So each individual particle, and I've got d of them, moves according to this recipe. They fly with the Hamiltonian flow, but at the end of the step I have to introduce this accept reject. But this accept reject is global. All particles talk at the accept reject, because I have to measure the aggregate change in energy. Okay? So the thing in squared brackets is the energy that I've gained for one particle. I have to sum over the particles, take the exponential, and then take the minimum. And this is what determines whether I accept or reject. So we want to, this is a random variable, of course, because everything will be random here. Well, h naught, but the xi's will be random variables. So this is a random variable, and I need really to see whether this is small or large. So the question is, how much energy do I gain when I integrate a Hamiltonian system by using the Fairley method. This is the key point. So we need to really to estimate, not in the sense of probability, but in the sense of analysis, the energy increment for a single particle. So this is my initial location. This is the solution of Fairley. This is the change in energy. It would be 0 if Fairley were exact, or if I could avail myself of the true flow. Then this delta would be 0, and I will sum over particles. It would be 0, and acceptance once I would always be accepted. But as soon as I start committing errors in energy over the different particles, this sum will be large, and A will decrease accordingly. Yes, Sivert?
But why on the right hand side?
Sorry?
A or X, not Y. On the right hand side, I don't see X.
X?
I.
XI, yeah.
Capital X and capital Y. He's asking for the Y.
Why? Well, I think you are following this very closely. Why? But it has been introduced. Why is the result of the proposal? But it wouldn't be necessary here. So just call this A, right? Why is the proposal? But you're right. I mean, I shouldn't have this. Thank you very much. I will change it for if I present this elsewhere. So we need we need to estimate this energy increment. Okay. So now I proceed as follows. I fix a position of a single particle. This is this small x. I take one step of not one step. I integrate with Fairley with step length h, and this will be the increment in energy, right? So that, say, this is my x, this is the Fairley, well, comes here with the Fairley, and I record the increase in energy when I use Fairley with the step length h, and I want to this difference is this capital delta that depends, of course, on my initial condition and on the step length. Right? Now, because the Fairley method is of the second order, and this is like a global error, I expect that this delta will be a quantity of the second order. And in fact, under suitable smoothness assumptions, it will not always be order h squared, but you will have an asymptotic expansion of this form. So my increase in energy will be h squared times a function alpha that depends on my initial point plus higher order terms, because this rho tends to 0 as h goes to 0 with each fixed h. But I will come to this later. So again, if I go from there, I gain energy, and this is the thing I'm really measuring, and this is an order h squared quantity. But of course, because I'm taking expectations, I'm not interested in what happens to a particular initial condition. I have to average over phase space, and now this is where geometric integration kicks in, because you see, if when I go from there to there, and this is a Fairley integration, I gain energy, in this case 0.1, as I said before. If I started from there, then I lose exactly the same amount of energy. So when one does averaging, due to the reversibility of the method, you get cancellation. So that overall, over phase space, the Fairley method conserves energy precisely. Well, there's a fly in the ointment, and that this averaging that I've suggested here was done with respect to the Lebesgue measure, but we are not interested in the Lebesgue measure. Our expectations are taken with respect to our target distribution, which is e to the minus h. So then what happens here? then you see I have to average with respect to the energy. This will mean that when I go from there to there, I gain energy, and I weigh that gain in energy with respect to the exponential of the minus energy there, and there is the same decrease, but I weigh it differently. And I will put less weight there, so that those two, once the weight is taken into account, don't cancel exactly, because they are weighted differently. So when I combine in couples, so this is twice the average. When I combine in couples, I get this, but this weight is weighed in a different way at the one extreme and the other extreme. Now I can rewrite that as that. So twice my average has this expression where I put this out as a common factor, and then you see this is my increase, 1 minus the exponential of minus delta. But then this delta is small, so this is approximately delta, so the average gain in energy with respect to my density, my target density, is not of the order of delta, is of the order of delta squared, because I get one factor delta from there, and this is also of the order of delta. To make this precise, I assume this other condition, C2, that delta squared over h to the fourth is dominated by a function that is independent of h squared. So when both of those conditions hold, I can prove this theory. If C1 and C2 hold, then the expectation and variance of this delta, which is the increase in energy for a single particle, they both behave as h to the fourth, in the sense that as I decrease the step length in the Fairley, mu over h to the fourth approaches a limit, and sigma squared, is the variance, over h to the fourth approaches a limit. And furthermore, this limit is half that limit. So this settles the behavior of the energy increase for a single particle. Now for the acceptance probability, I have to put together all d particles. And because in a single particle, on average, I gain h to the fourth, to get another one increase in energy, the reasonable thing to do is to take h proportional to d to the minus a fourth, because then I combining d particles, each gains h to the fourth, but then this will be 1 over h, and everything will come to be of order 1. So once you've chosen this scaling, then you can use a suitable central limit theorem to come up with the result. And here the thing I want to stress is that as you see, the ideas that come here are precisely those that some of you have used in geometric integrations and in Hamiltonian problems of reversibility and so on. Those are the key ingredients to deriving the results. So at the end of the day, this is the theorem that we can prove if those conditions C1 and C2 hold, and you scale the step length in the Fairley algorithm proportional to the inverse of the fourth root of the dimensionality, and this L is a fixed constant that you are free to choose, then the acceptance probability that you find will approach a finite limit. And this finite limit you can express in closed form in terms of the cumulative distribution function of the normal variable. So that phi there is just for a standard variable, the cumulative distribution function. So this is this phi. and the sigma is a parameter that appeared in the conditions that I had before. So this depends on the target distribution. This is the scaling coefficient between h and d to the minus a fourth. So this is a constant that I'm free to choose. Choosing, of course, a larger value of L takes h longer, and then this will be the limit acceptance probability that I get. As I said, this phi is a known function, L is my scaling, and sigma depends on the potential that I'm here reading with. Now, because I presented this for the Fairley, but you see that the argument only relies on your integrator being volume preserving and reversible. So for an algorithm that preserves a volume and is reversible, you can do the same. And if the method is of order 2 nu, then you have to scale L according to this. So that higher order schemes have even more favorable behavior of h as a function of the dimensionality. Now, what remains is as follows. For the theorem we had to hold, we need to check two hypotheses, C1 and C2. C1 refers to the existence of an asymptotic expansion, and then C2 is a technical condition on the behavior of the remainder. And of course, if you want to be mathematically precise, you want to relate the conditions C1 and C2 on properties of your target density that you could check in practice. Well, you can do this in various forms. Proving this is really a nightmare, all these estimates, but you can prove that if your potential is bounded from below and 4 times continuously differentiable with bounded derivatives of order 2, 3, and 4, so the first derivative needed to be bounded, and then you've got those either this or this integrability conditions, then C1 and C2 will hold for Fairley. And you can, if you are very patient, you can maybe derive similar results for higher order methods, but then you need, of course, more smoothness on V and more technical details, and those I don't think they are very important, and in any case, we haven't got them yet. So, what remains to finish the talk is the optimization of the algorithm. Recall that I told you that Roberts and his co-workers showed that they told us not only the correct scaling of h as a function of the dimensionality, but they also gave us those magic values of the acceptance probability that ensure that the algorithm makes as much progress as possible. So to finish the talk, I'm going to do the same for the hybrid Monte Carlo. So first of all, I need to point out that this combination L, recall L is the proportionality constants between 1 over 4th root of D and H. L times A of L is a reasonable measure for the efficiency of the algorithm. So this is a good candidate to quantity to a quantity that should be maximized for the method to perform well. Well, there are two proofs of this in the paper we've written, and they work along different lines. The first one is in terms of computational work. The work to compute a single proposal is proportional to t. This is the integration time over the step length. This is because, of course, this is the number of steps that you got to compute, and then the dimensionality. So this comes to this. For a given problem, the dimensionality you cannot change. So this is inversely proportional to L. But once you've made the proposal, you want your proposal to be accepted. So the expected number of proposals until the first accepted is, of course, varies in inverse proportion to the acceptance probability. So when you combine both things, you find that the work until your next acceptance grows like d to the 5 over 4 divided by L, A of L. So we really want to choose our L so that this is minimized. There's an additional proof, or an alternative proof, even more rigorous than this, in fact, in which you measure the distance as you travel in state space, and then you can show rigorously that by minimizing LA of L, you maximize the distance that you travel in a state space for a given value of t and a given dimensionality. So I guess this is the last slide. So from the previous slide, we have to maximize the efficient, which is this guy there. But for the acceptance probability, I got that formula in terms of this distribution function of the standard normal distribution. This sigma depends on the specific target distribution I want to sample with, and this L is the variable in our optimization procedure. Now, here, this is not tractable because this sigma is unknown to the user because it depends on the target distribution, on H, on T, and on the choice of mass matrix. So the trick here is in this combination to invert this function and to express not the A, the acceptance probability, as a function of L, but to express L as a function of A, right? So I rewrite this by inverting this function, and I come to this expression. Now what you see here is that this thing, sigma, that is unknown to me, is now out and appears in a multiplicative fashion. So it's not really necessary to know the exact value of sigma to maximize this as a function of A. And when you do this, you come to this value of A, which is 0.65. At this value of A, this lot is maximized, and therefore the efficiency is maximized regardless of the specific details of the target distribution and other parameters. So the conclusion is that if you choose the parameters for your distribution, your H, your T, your M, in such a way that when you run the algorithm, you see that the algorithm is accepting the proposals 2 out of every 3 times, then you are in good shape. And as I said, this has been proved under maybe a hypothesis that is very severe, but practitioners had found before that this works in practice in real, more realistic applications. So I thank you very much for your attention.
Could you comment on where T, capital T, enters in your estimates?
Yeah, this is something we have considered as well, and it's very important. So in this setting, T is not a good candidate to vary, because it's clear that the longer your T, the more expensive your algorithm, because you have to perform more fairly steps. So the benefits of having a larger T would be that by doing so, you should both get less correlation between consecutive steps of the Markov chain, and also this will give you some leeway to jump from a mode of the distribution as to a different mode of the distribution, as you were doing in the morning with the Helmholtz free energy. So I think this is an interesting problem. I think it has to be tackled with techniques quite different from this one. And if the organizers are good enough to invite us, either Andrew or myself, to a conference in 3 years' time, we might be in a position to present a result. But as of today, I don't have an answer to this.
So you're using the Verlet method is second order accurate. Do you need that sort of uniformly with respect to the initial conditions?
No.
Or uniformly with respect to the number of dimensions?
No. This is why the analysis is complicated, because I have to monitor the energy growth as a function of x, right? I don't assume that there's a uniformity in phase space. I have to keep track of the growth. So typically, if X is very large, the increase in energy will be large as well. Say for the harmonic oscillator, that would correspond in probability to the Gaussian. Of course, the farther away from the origin I am, the larger the energy increment, because it scales like the distance to the origin squared, right? But well, this makes for the analysis to be very complicated, because you have to keep track of all sizes. And this is the reason why we in what we wrote, we were able to identify specific conditions of V for the Fairley, that you got the fourth root of H, and we only hinted a more general results in terms of those conditions C1 and C2 for higher order methods. But I mean, we were not brave enough to do a method of fourth order or sixth order, because I think then the analysis just becomes mind-boggling, at least to us, maybe some of you.
Can you comment whether there's any CPU savings over Langevin if the computation of Hamiltonian is expensive?
Well, I mean, different. I'm not. I mean, my background comes really more from other parts of mathematics, but I think there are people in the audience that have carried out comparisons, and maybe Frederic can report on those. But I think that in practice, it's found that it pays when you've gone to. Well, sampling from the Hamiltonian to begin with or from the vector field is not an advantage when you compare with MALA or other algorithms, because also in those you need the gradient of the potential. So to run any of these algorithms, you need a subroutine that, if you say in a molecular dynamics setting, that you give this subroutine your configuration, and then you need to know the force in the molecule or whatsoever. So all algorithms use this. So the main difference with MALA is that in MALA you just take one step and you think whether you accept or reject. In the hybrid Monte Carlo, you take maybe, I don't know, 10 or 20 steps of length h, and only at the end of the 20 steps you make a decision as to accept, reject. And if you reject, of course you reject an amount of work that is much larger than what you've rejected in MALA. But I think people who have run experiments, and Frederic Legault has published at least a paper, maybe more, I don't know. They found that it's advantageous to use this Hamiltonian approach.